Okay, so everybody able to solve it, right? From how much hydrogen needed to 10 gram of ammonia. So here hydrogen is B because this is unknown. The known is ammonia, which is A. So gram of A to mole of A, then multiplying by coefficient from the equation, and then multiplying by molar mass to get the gram of hydrogen. Mass, how much means it's a gram, amount in a gram. So let's solve a problem in here. You have propane, C3H8, this is a propane. This propane reacting with oxygen. Reacting oxygen means burning, combustion, and forming carbon dioxide and water. The question is, how many grams of carbon dioxide producing from 20 gram of propane? So propane gram is given, and you have to calculate how much carbon dioxide. As I said, you have to know the formula, how to apply this equation. You have to know which one A, which one B. So A is the one known, right? B is unknown. So which one A in here? Propane or carbon dioxide?
Propane.
A is the carbon dioxide. A is the propane because A is given. B is carbon dioxide, which is unknown, right? So start off. If you go back to the formula, is start off whatever given A. So you have A, which is gram of propane. So can you do that?
Yes, we can try.
Who can do that? You want to come to the board? Okay, come on. Write a big number, okay? Big letters, so people can see. So it is good. We solved together. You guys work together. Now, kind of last problem that you're solving. Then we'll move on to limiting agent and percent yield. Question? Okay. That is a bigger number. I can't see.
Sorry.
Yes, thank you. So, what is the key idea in here? You have a gram converting to the mole of propane, then multiplying by coefficient, then multiplying by molar mass. Mass of carbon dioxide.
Oh, okay.
Unit mass, 44 gram of carbon dioxide. 44 gram of carbon dioxide.
Oh, okay. For moles?
Yes.
Okay.
So, she did right. So we have a gram of A, which is 20 gram. Then dividing by molar mass, get to the mole. The mole multiplying by coefficient from the equation, you see 1 mole propane and other one is carbon dioxide. So I have 3 carbon dioxide. So my coefficient is 1, coefficient is 3 for carbon dioxide. And then multiplying by molar mass of carbon dioxide. So what you need to do, very first you always calculate molar mass of propane, C3H8, right? So calculate molar mass of propane first. So 12 times 3 plus 1 times 8, 44, right? And then calculate molar mass of carbon dioxide, which is 12 plus 16 times 2, which is also 44. So that's your calculator, right? So 44 gram of molar mass for propane 44, carbon 44. So you're dividing by molar mass of propane to get the mole of propane. Then multiplying coefficient, then multiplying the molar mass to get how much carbon dioxide you get. So which is
grams.
it's changing. Where it is in the right side.
Yeah, I get 60.
Yeah, there you go. So you got 60. So you multiply on the top 20 times 3 times 44. In the denominator you have 44 times 1 times 1. So whatever you get gram of carbon dioxide. 60? 60, yeah. 60. So is 60 is correct? It is correct, right? Because you have 3C figure. So 60 should not be correct. You have to be 60.0, right? So I have in the PowerPoint you have solved this one. So now we can go to the limiting reagent. What is the limiting reagent? Leftover. Sounds like leftover, limiting. No, actually.
Well, what I was saying is whenever the equation is balanced, whatever's left over is eliminated, right?
So, any other idea limiting reagent?
So that was wrong.
Let's get second thought. Limiting reagent. What is it? Which ran out earlier. Which is ran out earlier, right?
You need, that's what you need that. You want something. Okay.
Okay. So when you have a reaction, right? Chemical reaction going on.
Yes.
When you have a chemical reaction, you have a 2 reagent or 3 reagent, you accept that one of them would be finishing earlier than others. If possible. Not necessarily that always all 3 or all 2 of them in the same number of mole ratio as needed. So one have to be limited. One always should be limited. So the one is limited, that's going to be finishing earlier. The one is more, that's going to be excess. The one limiting earlier, the one is limiting, which is finishing earlier, that determine the amount of product you expect. So limiting reagent is very important to know because that is the one will tell you how much product you get. Let's get an example. For instance, all of us plan to have a race in the street or a soccer field. So when you're running, everybody thinking have a race policy because it's a friendly race. It's not a race of getting medal or cup. So friendly race, you plan that hey, we all will be running together. And if anyone is weaker, we're gonna wait for him or her so that we can run in a friendly race running together. So you're all running together and then everybody is looking at me. Say, hey, Dr. Haque is the one weaker, he's a fatty guy, so look at him. So I am the weaker, I'm the running slower, everybody is following me because I'm the one determining the race of the pace of the race. So I am the limiting reagent because if I cannot run, you guys cannot run. So I am the limiting of this group, limiting run out of the group because I stop, you guys need to stop. I ran out of my energy, the race stop. So that's what it is, limiting reagent. So let me go, right? So limiting stop, the reaction will stop, right? So, and limiting reagent is very important because that determines the theoretical yield of the reaction. Let me go one hypothetical way, one like live example. You are hungry mid of the night, right? You jump into the kitchen and got some cheese and bread. Get a couple of sandwiches, right? So let's see what you got. You got a couple of bread sandwiches. How many you got? And before you eat, you're thinking one sandwich needs 2 bread, right? And then you start. No, it's on the computer, the PowerPoint. Nobody did that. I know, we're looking at the back. Nobody did that. So, yeah, she thought someone doing it behind. Oh. So, you're making sandwich, you see? Got it? Okay. So, you're making sandwich with the 2 with 1, right? And you looked at how many bread you have. 6 bread and 4 slices. So, tell me how many sandwich you can make? 3. So, when you saw that, hey, you got a lot of bread, I got 6 bread. But I have, oh my God, I got less cheese. Is it true? No. Which one will be left over?
Cheese.
Bread.
You see?
Cheese.
Cheese is going to be left over because that is excess.
That's true.
But it looked like bread is 6. We have more bread than cheese. Actually, it's not.
Right.
Because depending on the ratio of
The bread to cheese.
bread to cheese needed to make a sandwich, which is not actually the 1-to-1. There would be 2-to-1. That's why the limiting would be bread.
I was right.
Oh, you said limiting bread?
Yes.
Yeah.
That's why I was confused. I said, wait a minute.
We all are right actually. Everybody focusing, working together, solving problems. Actually, I'm lacking the class. You guys very, working together, which is good. Very good. Working group always helps to learn. Okay. So limiting is the bread. So what do we see? For instance, this reaction we have ammonium nitrogen. So for instance, ammonia, for making ammonia, 1 nitrogen and 3 hydrogen needed, right, to make 2 ammonia. If I have a 5 gram nitrogen and 5 gram hydrogen, you cannot say that, or if I say 15 gram hydrogen, 5 gram hydrogen, 15 gram nitrogen, you cannot say that, hey, I got it. This is the limiting, which you can see, we can prove from here. The amount is not the limiting because reaction go mole to mole. And also, we have to look at reaction coefficient. So let's see how that works. How can you determine the limiting reagent from a chemical reaction? Step 1, from the given amount, calculate the product. For instance, you have a 2 reagent given, right? Let me take off this part. So, for instance, I have ammonia, 15 gram and 5 gram, right? Then, from both of them, I will be calculating how much ammonia can produce. And you know how to do that, right? Gram to mole, mole to mole, mole to gram. So, we're going to be calculating in step 1, from both given amount, we'll be calculating the product you're expecting. Then, the one will be less product. For instance, this giving us 5 gram of ammonia, okay? And this gives us 6 gram of ammonia. So 6 gram of ammonia, right? So the one giving less product, that is the limiting. So this is now limiting. Why? Because the one giving less product.
Where you get
I'm
5
just-
and 6 from?
I'm just making it up.
Oh, okay.
I'm just making 5, 6, I'm just making it that. What if it gets calculation gives you 5 and this gives you 6, as we said. Get the product from both reactants. And how do you do that? You know, the gram to mole, mole to mole, mole to gram, right? You know that part. You're already doing this calculation a couple of times. So let's go one more example, more practical way. You have ammonia, carbon dioxide, making urea. So look at that. You have 2 reagents given. Ammonia is this amount, carbon dioxide is this amount of mole. You calculated, multiplied by coefficient, right? You know that by this time. And then you saw how much urea can produce, right? And look at that, the one got less amount product. So this carbon dioxide one giving the less number of product, less amount of product. In mole, we haven't calculated in gram yet, I'm just showing in mole. So the one giving less product, that is the limiting reagent. So carbon dioxide is the limiting reagent in here. Okay? Solve this problem. Everybody do that. You have a two reagents, zirconium chloride and magnesium. The question is, how many moles of zirconium metal can be produced from reaction mixture? So before I go, before I let you work, remember that this is the limiting here, right? And what is the right product? This one or this one? The one is the less amount, that's the right product. Because if this is limiting, that determines the amount of product. This ran out, it cannot produce more because reaction will stop. Limiting means limiting ran out, reaction stop. So limiting is the one giving the right product. So now you look at it, what you have in here. You have zirconium chloride.
What's the question?
Look at that. How many mole of zirconium metal can produce? So which one is B? This is the B, right? Product. You have it, this one and this one given. Zirconium chloride ZrCl4, 0.2 mole given. Everybody please work in a group.
You changed it. Oh.
Okay.
If you're not doing the board, take everything off. Clean the board.
Yeah, because you have two different amounts. You gotta have,
You have to do it twice, yeah. So you do not need to copy anything because this is going to be posted for you. You want to do that? So if you go back, look at it here. So you have 2 moles given, right? Someone I said, there is a question someone. So 2 reactant. So 2A. There are 2 calculations. 2 product. The right product is the one which is less. Okay, that's okay. Because 2 reactants. Now we go back in here. You see, 2 reactants, zirconium chloride and magnesium. Both is given. One is 0.2, other one is 0.5.
The example.
Not anymore. So we can't see, bro. We can't see that. But no, it could be bigger.
Make it bold.
Yes, sir.
Very triple. So. Not even enough, right? Bigger than that. Bigger, bigger.
Yes, sir.
Try to. Yeah, then I had to get rid of the CL. And it's dark, really dark. I wish I could turn off this light, but all are together. All are single, one switch from the other.
Very good. He is doing very good. He started off 2 reactant, which is 0.2 mole of zirconium chloride, 0.5 mole of magnesium. You see, 2 reactant. So for product is zirconium metal, right? It's a 1. You see, 1 mole.
It's one.
Yeah. So 1 mole of zirconium in the top.
Yeah.
Yeah. 1 mole of zirconium. So 1 mole of zirconium over zirconium chloride is also 1 mole. See? So 1 mole of zirconium.
It is. Actually. I think it's just because you go through the process. They want to do the steps.
Wait,
So
what?
we gotta make sure that-
1 mole over 1 mole, that's how it goes?
Okay, let me take over. So 0.2 mole zirconium is a given, right? So you have 0.2 of this one and magnesium 0.5 is given, right? So we're gonna be calculating this to this, also this to this, right? And the one giving less product, that's the product. That's actual. That's called actual yield. That's actually theoretical yield, because we're calculating this theoretical. So to get the right product, we first started off what was given, then multiplying by coefficient, because we are in first step. You don't need to do, because things given in a given in a mole, you don't need to the first step. We are in the second step. Mole A to mole B. This is mole A, this is mole B. So mole B is zirconium, which is, you see from the equation, 1. And from equation you see zirconium chloride is also 1. So 1 over 1. Right? Then that means if you cancel out, you get same 0.2 mole of zirconium. Zr. And the second part is 0.5. Zirconium chloride, magnesium is 0.5, right? So then 0.5 mole of magnesium times magnesium to zirconium. So 2 mole of magnesium, you see 2, but zirconium is 1. 1 mole of zirconium, you see. So that gives us 0.25 mole of zirconium. See? So now we can see which one is less for. This is 0.2, this is 0.25. So this is the answer. Because that is asking how many mole of zirconium can be produced. The one is less, that's the right answer. So now the question is, if there is a question, which one is limiting reagent? Zirconium chloride or magnesium? Zirconium chloride. Because the one giving less product, that is the limiting. Done? Okay. Look at one more problem. Ammonia and carbon dioxide producing urea and water. So in this problem, you have a 10 gram ammonia, 10 gram carbon dioxide. So to produce ammonia, question is how many grams of excess reactant left for that reaction? So which one will be excess in here, in this reaction? So this is the limiting, right? That will be excess. That will have some excess because being excess means all of the molecule, all of the reagent will not be used up. Because as soon as it's ran out, this finishes, the reaction stops. But this is not finishes yet. This is the only one finished as a limited.
Because there's 0.3 units left of that.
Yeah, we don't calculate, we don't subtract directly. We have to see by mole to mole comparison. We'll do that.
Because some of them are two.
Look at here. So first hand you need to calculate the molar mass of all of them, ammonia, carbon dioxide and urea, right? And then let's see how much you get from ammonia, how much you get urea from carbon dioxide. From ammonia I get, you see, from ammonia I get 17.6 gram. And from carbon dioxide I get 13.6 gram. So which one is limiting?
The 13.6.
Carbon dioxide or ammonia? Which one is limiting?
Carbon dioxide.
Carbon dioxide.
Yes.
Look at that. We started from same 10 gram, 10 gram. But now we see one is actually less limited based on the product. Less product. This is the theoretical yield. This is the right product from this reaction we're expecting, and carbon dioxide is limited. So this will be produced. And then how much you have left? So you have to, how much you have left, you have to calculate from carbon dioxide. Comparing with a mole of ammonia, then you see how much ammonia used up. That means this amount ammonia will be reacted. You have to compare mole of carbon dioxide to mole of ammonia. And then the left will be the remains. Okay? I will be posting the PowerPoint for you. You can review. So we have a couple of practice problems in the earlier lecture, so I will not be repeating anymore. And we have one more problem in here. And then this is the theoretical yield. The one limiting is calculating, the producing, that's called theoretical yield. And what is percent yield? Percent yield is actual over theoretical. Theoretical yield is the one we calculate. What is the actual? Like for instance, you
actually get.
Exactly. Actually, you get an experiment. For
I guess you
instance,
can say actually because it's like a double.
yeah,
Say
you planning
your yield,
you
what
plan
get.
today to be in the class 8 o'clock, right? How many of you could? No, many of you did not. Maybe, or some of you. So you plan to be at 8 o'clock. You are 8:05. That means you're actually 5 minutes late. So you are 5% behind, right? For instance, you are 5 minutes behind.
So -5.
So yeah, I'm just giving an example. It's not
5
applied.
minutes will be the actual.
So calculation will not be the actual way. Okay, let's see. Let's see more similar example. It will be more clear. For instance, you're doing an experiment, right? You started a reaction. You wanted to get 10 gram of urea. Wanted to produce in the lab. So you plan the reagent for 10 gram. But when you put in the reagent, your yield theoretically is 10 gram, but you actually got 9 gram.
Which is your actual.
But what did you want, and why 1 gram less? Why not 10 gram? Because there is some energy always going to different direction. Energy cannot be destroyed, but energy always converting to different energies. So you started a molecule, carbon dioxide and ammonia. Maybe some ammonia got burned out. Some made some byproduct, you see? So actual yield always less. Actual yield always fraction of theoretical yield. Theoretical yield, the one you plan for 10 gram. but actually you got 9 gram because some is always get lost. So that is the percent yield, actual over theoretical. So whatever you calculate, that's the theoretical. For instance, look at the equation. You have 10 gram of ammonia, 10 gram carbon dioxide, and then you expecting to get 13.6 gram of urea, right? You actually got 9.3 gram. Tell me which one is actual, which one is theoretical?
9.3 is the actual.
Yes, 9.3 is actual, yes. Theoretical yield? 13.6, very good. So, look at the 9 point, so that means,
Yeah, like what you theorize, what you want it to be, that's your theoretical.
so to calculate percent yield, then percent yield, you calculate the actual times actual over theoretical. And times 100%, right? So 9.3 gram was the actual, but theoretically you expected 13.6 times 100, which comes as a percentage. Then you calculate that, that will be coming as a percentage. Okay? That is how you calculate mole to mole, limiting reagent, access, how to calculate percent yield, and stoichiometric. These all are stoichiometric calculations. Remember, stoichiometry have to be in a chemical reaction. It have to be balanced chemical reactions. That's the one thing. Sometimes students ask, I get the questions a lot that, for instance, this is a chemical reaction, right, in here. I see 2 in here. Question is it balanced chemical reaction or do I need to balance?
No.
You're right. Because whenever you see some coefficient, you expect that this reaction is balanced out. There will not be any confusing part that, hey, it's halfway balanced. If you see coefficient, it is balanced. Because you need to be balanced chemical equation to calculate product and reactant, reactant to product, or product to reactant. So, if it is any coefficient, it is balanced. If it is no coefficient for reactant and product, you gotta think again. Go back and check whether balanced or not. Okay? That's all for today, guys.